In this video, we're going to cover Unit 2, Part 2, Lesson 1, and we're going to introduce a few more derivative rules. For this video, I'd like to talk a little bit about how the limit definition is used to establish these derivatives. And this will be just our last example of using the limit definition to establish these rules. Keep in mind, though, that this limit definition or some sort of similar proof has been used to establish all of the derivative rules that we use. We don't do that in this class, but it has been done by other mathematicians in the past. So the limit definition said something like this: the derivative of a function is equal to the limit of that function as h approaches 0. Oops, let me be a little bit more careful here. The limit as h approaches 0 of f of x plus h minus f of x divided by h. So as this difference quotient is evaluated with h approaching 0, then the end result is indeed the derivative. So I'd like to use the limit definition to establish the derivative of these two functions. I'll walk through the first one and let you try the second one as well. So again, we know that f prime of x will be equal to the limit as h approaches 0. I'm going to switch to a lighter weight pen here, of f of x plus h minus f of x divided by h. And in this case, that would be the limit as h approaches 0 of 2 to the x plus h power minus 2 to the x power divided by h. That was simply our substitution. Now, what I hope you would recognize here, or maybe with a little convincing, you might recognize that this expression, 2 to the x plus h, is just an example of our law of exponents. And we know that, for example, if I had a base x to the 5th power multiplied by x to the 6th power, that would be the same as adding the exponents together and obtaining x to the 11th power. Well, as you notice here, we've got the sum of two exponents, so we essentially have something that looks like this middle guy, and if we work backwards, we can separate this into a product of two components. So this would be 2 to the x power times 2 to the h power minus 2 to the x power. And that may not be immediately obvious why we do that, but it should make sense to you at this point. Sometimes we try these tricky math steps and see where that takes us. What I particularly like here is that this 2 to the x power and this 2 to the x power are common factors for these terms. So we now have the limit as h approaches 0 of 2 to the x power. If I factor that out, I'm left with 2 to the h power minus 1 all over h still. Now, unlike our other limit definitions, at this point during the factoring process, we couldn't really get the h in the denominator to cancel, and we still can't do a direct substitution. In order to continue with the analytic method to identify this limit, we would have to change some variables around and try some other tricks. But that's okay. We're going to avoid that, and perhaps I can make an argument for our objective here with a table of data. So let's use this definition and see if we can evaluate the derivative at 0. So let's just remind ourselves real quickly here. We've got f of x equals 2 to the x power. That's an exponential function that looks something like this. And so I'm curious, what is the derivative, or how steep is the graph right at this point when x is equal to 0? So that's what I'm going to try to answer with this derivative down here. Well, that would be equal to the limit as h approaches 0 of 2 to the power of 0 times 2 to the h minus 1 divided by h. And of course, 2 to the power of 0 is equal to 1, so this single fella seems to disappear, and we're now left with 2 to the h power minus 1 over h. If I make a table of data with h values that are getting closer and closer to 0, I should be able to approximate what this result will be. And so off to the side, even to the right of our second example, I'm going to build a table that looks like that. And for h values that are approaching 0, I might choose negative 0.1, negative 0.01, negative 0.001. And from the right side of 0, I might choose 0.001 again, 0.01, 0.1. And this is going to let me find the derivative at 0 for f, and eventually it's going to help me find the derivative at 0 of g. Separate these columns. And now I'm just going to switch to a calculator and evaluate this function with different h values. So if you recall, in these TI inspires, we can store numbers in place of letters. So let me build the function first. Control divide. We can write 2, whoops, let's try that again. 2 to the h power. We can actually write the letter h here. Minus 1 over h. And the calculator doesn't know what's going on here for the letter h. It's written the letter as an italic number, so it's not going to do anything for us right now. But if I take the number negative 0.1, I can store that with the store command. I have to press control variable. That's the store command, and I can store this in place of letter h. Now, if I repeat the command from the line before, the h is a bold letter. And when we press enter, we see that with an h value of negative 0.1, we get a derivative result of 0.6697 when rounded. 0.6697. I'm going to do the same thing for 0.01. So negative 0.01 is going to get stored in place of, stored in place of h. And now I'm going to repeat the prior calculation. Remember, we just press the up arrow until this is highlighted. When it's highlighted, you tap enter and it copies it down. This time when it executes the command, h is going to be worth negative 0.01. And now we get a data value of 0.6908. And we can continue this process. I'm going to pause the video and fill in the chart for function f. And here's what the rest of the table looks like. Now keep in mind, we're trying to find out what happens as h approaches 0, and since that can't be evaluated directly, we're looking at, or we're kind of estimating what the number would have been right about here. So we're looking at these two results specifically, and since there's a pattern that's trending towards this result, then I think we can focus on these two. If these numbers surrounding it didn't seem to support the tendency of the function results, then we wouldn't look so closely at these two. But we're definitely increasing from 0.66 on the left and decreasing from 0.71 on the right, and we're tending towards 0.69 something in between 0.6929 and 0.6934. Put that on pause for just a second, and I'd like to try the same thing for this function. The derivative is, not of f of x, but the derivative of g is equal to the limit as h approaches 0 of, g of x plus h minus g of x divided by h, which again would be the limit as h approaches 0 of 3 to the x plus h power minus 3 to the power of x divided by h. And in all honesty, the remaining expression is going to execute just the same way. And so we can now claim that the derivative of g prime at 0 would be the limit as h approaches 0 of 3 to the h power minus 1 divided by h. Sorry, this minus 1 is on the same level here. I was distracted because I noticed that I missed something over here. I should have included that limit notation. So shame on me for forgetting that. I'm going to correct it since I can. I would recommend that you make a note of this as well, because the limit notation should be retained even through this point here. Well, with this new function for g prime of 0, we can now do the same thing we did a minute ago. We can rewrite our function. Instead of 2 to the h power, call it 3 to the h power. And I'm going to ignore this result for a second because this isn't the h value that I wanted to start with. I'm going to store the number negative 0.1 in place of h. And I'm going to execute this expression. We get 1.0404. So when h is negative 0.1, we get 1.0404. And again, we can go through the calculator and change the h values to each of these numbers that remain. Go ahead and try that again on your own. See if you can establish the remaining numbers for g prime at 0. And here are the results again. Now, keep in mind that we're talking about this function now. 3 to the x power is our definition of g. And now it's going to look a lot like the other graph, but it's a little bit more steep here. We should know that because of our understanding of exponential functions from last year. But these two graphs are going to look virtually the same, but this guy's a little bit steeper because our base is 3 instead of the base being 2. We can also support that claim by looking at the derivatives that are occurring here. We're saying that, if h were equal to 0, as h approaches 0, we're seeing a derivative of that first function around 0.69, and we're seeing a derivative of the second function around 1.1. So the steepness, or the slope, is approximately 1.09 in the second graph, and the steepness, or the slope, of the tangent line is about 0.69 in the first example. So this steepness is less than that steepness. And the picture below is meant to illustrate this thought. The red graph is our slope, is our equation y equals 3 to the x power. This is our g of x function. And the black graph is our f of x function. And so the red function is a little bit more steep than the black function. And so in the age before Twitter and Instagram and Snapchat and TikTok and all that stuff, people had fun with little puzzles like this. And some mathematicians started questioning themselves. They said, okay, when we had a base of 2, our slope was a little bit less than 1. When we had our base of 2, our slope was about 0.69 something. When we had a base of 3, we had a slope of 1.09. Can we find a number, a base value, somewhere between 2 and 3 so that the slope of this dotted line, the slope of the curve, is there a curve somewhere between, and I'll try to make that stand out with a different color here, is there another exponential curve somewhere in between those two so that its dotted line has a slope of precisely, exactly 1? Is there a number in between there? Well, as it turns out, there is. There's a precise number between 2 and 3. In fact, it's going to have to be a little bit closer to 3 than it is to 2 because 3 is, the slope here is pretty close to 1 already, and relatively speaking, this number is pretty far from 1. So the end result of the number is pretty close to 3. If I'm not mistaken, it's 2.781828482459. I'm trying to do the calculation in my head here. I think that's pretty accurate. I'm just kidding. I was looking at the screen ahead. The number e is what we're talking about here. The number e, if you remember that base e, the natural base e, that's the magic number here. So this is the number that's slightly bigger than 2 but less than 3, so that when it's placed into the function, or when it's used as a function to create a graph, the slope right here at an x value of 0, the steepness at that specific point is precisely and exactly 1. And while this number e is named after the mathematician Euler, I don't think he was the one that actually established this definition. I'm not entirely certain who was, but Euler was a mathematician in the 1700s, and calculus was just really invented in the mid to late 1600s. So all the mathematicians of their day were kind of advancing these techniques in calculus, and Euler was one that did that. In fact, Euler's the mathematician that coined the notion of function notation. It's because of his work that we use f of x to this day. And while this particular decimal value over here is a non-repeating, non-terminating decimal, it does have a definition, and if we wanted to compute what that value was to an extended number of decimals, we can use this formula here. We can evaluate the limit as x approaches infinity of this particular expression. Now you can imagine what happens as x gets super large. We get 1 divided by a number that's very, very large, so this component essentially equals 0, but the sum of 1 plus a number slightly bigger than 0 raised to an infinitely large power does some weird things as well. And as it turns out, as x gets larger and larger and larger, this calculated result really only approaches 2.718282, etc. So anyway, the magic number to answer the question that we started this conversation with is e. And the limit as h approaches 0 of e to the x power minus 1 over h, I'm sorry, e to the h power minus 1 over h, is going to equal 1. So we're not talking about a base of 2, we're not talking about a base of 3, we're talking about a base of e, which was this 2.71 number. This slope at an x value of 0 will be precisely 1. So one more time, if we use the limit definition, and you'll notice that the Leibniz notation for a derivative is used here. We're saying the derivative with respect to x of the function e to the x. This notation was used in place of saying that, say, f of x is equal to e to the x, and we need f prime of x. So we could have said that. We could have defined the function f of x and asked for the derivative of f using Lagrange notation here or Leibniz notation here. And if we use that limit definition one more time, the third time in this video, the process is essentially the same. We're getting to the point where we can say that the derivative f prime of x is equal to the limit as h approaches 0 of e to the x power times this expression, and because of our power rule of limits, I was able to separate that. The reason why I separated that is because the definition just a second ago, right above this, said that this particular limit here, the limit as h approaches 0 of e to the h minus 1 over h, this whole thing was equal to 1. That's exactly what this definition was saying. The limit of this expression is equal to 1, so I make that replacement, and now what I'm left with is to say that the derivative of that function is equal to the limit as h approaches 0 of e to the x power. Well, in this phrase, h is the variable that's being adjusted, x is just a numerical value. These are not both variables here. This is the variable, this is essentially a constant. So the limit of a constant is that constant itself. The long and short of it is that we have just now proven, albeit with some skipped or missing steps, we've just proven that f prime of x, as long as f was defined as e to the x power, is indeed e to the x power itself. So that to me is very interesting. What we're saying is that a derivative of a particular function is the original function itself. And if we think about what that means in terms of slopes, we're now saying that if I pick any point along this orange curved line, and that's a bit of a mess, so maybe I'll just recreate the sketch over here. So if I had that e to the x power graph, again, it looks like the others, we just have a slightly different slope here. But what we're saying is that if I needed to find the slope at any point on this graph, all I need to do is substitute the x value, the position of x, into the original function, and that function value will tell me how steep the graph is. So not only is it an interesting derivative at this position here, by the way, e to the 0 power is equal to 1, right? So e to the power of 0 is 1. We just said that that's the slope of this line. This line has a slope of 1. Well, this position here, when x is 1, e to the first power is equal to e. The steepness at this point is going to be e. The steepness at this point is e squared and e cubed and e to the fourth power. No matter where we are, if I want to know how steep that curve is, all I have to do is plug it into the original equation. And that's pretty interesting. A function's slope is equal to its own function value. So that was one of our derivative rules that we filled in on the other sheet, and derivative rules that follow along with it are here, 11, 12, and 13 on that sheet as well. Rather than going through the proof and explaining why they work, we can just accept them at face value and continue to use them throughout the class. I think this is a good stopping point for this particular video. I'll create a second video to talk about the remaining 2 points of note in this set of lessons. Thanks for watching.